Okay, so in this video we look at gravitational potential energy associated with an object as it changes its position relative to Earth, but now those changes in position are quite large in relation to the radius of the Earth, and so we can no longer assume a constant force of gravity like we've done before. So now we have a force that is variable. It varies inversely with the square of the distance between these two bodies, and so we have to take into account that variable force when we start looking at the energy associated with that position. A quick review on forces and energy for objects near the surface of the Earth. If I take some block and I lift it some height h from the tabletop, I know that the force of gravity is fairly constant here over a small change in elevation. So the force of gravity again would be mg. The work done by gravity as I lift that object up would be mgh, but it would be negative since the work done by the force of gravity rather is in the opposite direction of the height I'm lifting it. So this set of equations that we developed and the concepts here were fairly straightforward. This is a little bit more involved because we have a variable force of gravity. Now I want to try to take a look at this picture and see if we can understand how we might apply this variable force to an object that's moving in some sort of path. In this case it looks like it's some sort of curved path from point 1 to point 2. It's a little bit hard to understand what this image is showing here and how it relates to the equation that's hidden here. So I want to, before I show you this equation, I want to sort of take this diagram and change it a little bit. Sort of hard to do this on your own sheet there if you're following along with me, but I'd like to get rid of some of those arrows and just see what happens as we move an object from point 1 to point 2. Okay, and so let's draw a couple of I'm going to draw a couple of like curved lines here that sort of should be parallel to the surface of the Earth there. And so let's just keep going out here. I'm going to try to equally divide this into like three different elevations, if you will, all trying to match the curvature of the Earth. It looks like one of those was off a little bit, but that's okay. So I'm going to try to divide this up into sort of like these little quadrants, if you will. Maybe it looks like a baseball diamond or something like that. Now, as that object is moving from point 1 to point 2, let's go ahead and define some directions here. Let me go ahead and say that this direction is sort of like in the R direction, so sort of away from the Earth, sort of pointed right away from the Earth. And then let's say that we have some motion this way. Let's use some different colors here. So now we're going to move along this line to get to this point. Okay, so we sort of envision that what we're doing is we're doing all work here as we move it away from the Earth. All of the force that we exert would be doing positive work. The Earth would of course be doing negative work. And then as I move it along this, sort of like this line here, this arc, the force of gravity does no work since it's always perpendicular to the way the object is moving. Now we could do the exact same thing up here. Let's use blue again for this one. So now I'm at this particular point, and this time I'm going to have it sort of be directed this way. And again, this whole idea here, this blue line is sort of representing a distance straight away from the Earth, so sort of perpendicular to the Earth's surface. And then of course we're going to move right along here, along that line. And again, work being done here, no work being done there. And then finally we do one last little bit here. This one again is going to be sort of perpendicular this way. And then this last little bit moving right along here, so we get to that particular point. Now the reason I divided it up into sort of those three segments is that since the force of gravity is varying as I move great distances away, we can sort of consider each like little section of here as sort of a constant amount of force acting through some distance, and then that force acting perpendicular here, and so all the work being done here, none of the work being done there. If I wanted to determine the total work, I would just simply add up the work done in each one of these three segments. Now, let's see if we can't I'm going to use a little bit of color coding or a little bit of shading to try to understand why we will integrate this function. So let's see if I can't do that here. Let's see, I'm going to make this a little bit bigger. Got some gray in there, and so if I were to consider this entire like baseball diamond, if you want to think of it like that, as a region of space. Then I'm going to take this next section and I'm going to sort of highlight this portion again. And then I'm going to come down to this one, highlight that portion. And then finally, I'm going to take this last one and I'm going to make it even a little bit darker here. And so my goal here, what I'm trying to show, is that sort of like the density of the screen that you see here, the density of that shaded region, sort of represents like the strength of the gravitational field. And so here I have a really strong gravitational field. Okay, so I'm going to make that BG. Here it's a little bit weaker. Here it's a little bit weaker still. And then finally it just keeps getting smaller and smaller as I go out. So we can't just use a constant force of gravity like we did over here. We have to deal with a force that is varying. Okay, and so that's that idea. Now, that might help us understand what we mean by this little r hat. This r hat represents sort of a unit vector in the direction of like the radial line, the distance, sort of a line connecting this particular motion with the center of that object. And so r is sort of, r hat rather, is sort of changing in direction. It's always going to be perpendicular to the surface of the Earth. And again, that's hopefully will help you understand when we go to integrate. We're going to get an equation that looks something like this. We know by definition the work done by any variable force would just be the integral of F dot dl. In this case, the force due to gravity is in the negative direction or opposite direction of the way that I'm moving. And so this would be the way that we would compute the work done as an object moves between position 1 and position 2, so from here to there, with a variable force. Now, this hopefully will help you understand this r hat dot dl is actually going to be replaced now with this thing called, I'm going to take this right here, this portion right here is actually dr. Now, what do we mean by dr? It's probably easiest to understand by going back to the original diagram, so the one that we started with. Let's take a moment to clean this up and get rid of some of those things that I had done previously. So, let's see, this is out of there. This being replaced with dr. So, what is dr? If we come back to this thing here, remember r hat sort of represents the unit vector that's pointed sort of radially away from the center of the Earth. Okay, so it's sort of along that perpendicular that we were showing before. So that direction of r hat sort of changes based on where I am here and what my path looks like. dl, which is a part of this equation as well, sort of represents the instantaneous like positional change of my object as it moves along this arc. And so when I take the dot product between them, remember the dot product says how aligned are these two vectors. When I take the dot product between r hat and dl, I get this thing called dr. Now that value right there, dr, is important because I'm going to be integrating this function over the r variable. So that numerator needs to be transitioned sort of into a dr, and that's where that dr comes from. So why do we integrate? Because the force is variable, and we need to be able to sum up all of those little pieces of work that we do along that path. So hopefully that helps you understand what we're doing with this equation and why we need to go through that integration, and very importantly, what's going on with these r hat and dl vectors.